So it's a pleasure to introduce the next speaker, Brayan Ferreira from Universidade Federal do Espírito Santo. And he will talk about ECH spectral invariants and applications to Reeb flows on RP3.
Okay, so can you hear me? I want to thank, first of all, the organizers for the invitation. It's really a pleasure to be here. Like a few months ago, I was just a PhD student here, and in addition, Marta was my master advisor at UFES, and now we are colleagues in the department, so yeah, for me it's been great. As Leonardo said, I'm going to speak about the spectral invariants on ECH and some applications. So ECH has been shown to be very fruitful in understanding 3D Reeb dynamics. And I'm going to start to recalling the setup and the features. So we start with a 3 manifold, which is closed oriented. And then we took a non-degenerate contact form. So as it appeared in other talks, I think Miguel Abreu defined this properly. We have the Reeb vector field, naturally induced by the form, defined by the form. And then a form is called non-degenerate when you take a wave orbit and you consider the contact structure. So this is the kernel of the contact form. And then you look at the differential along of the flow along the orbit. So this is a linear symplectic map. And then you can classify the orbits by elliptic and hyperbolic, looking into the eigenvalues of this map. So this is non-degenerate when 1 is not an eigenvalue. And then the form is non-degenerate itself if all the iterates, all the Reeb orbits, for me, Reeb orbit is a closer trajectory of the Reeb flow, and are non-degenerate. And the orbit is elliptic if the eigenvalues lives on the circle, and hyperbolic if it lives on the real numbers. Okay. So we also fix a singular homology class, say gamma, and a generic symplectization admissible almost complex structure on the symplectization. So this is quite standard for doing contact homology. And then we can define the chain complex. So ECC is the chain complex for the ECH. Is the Z mod 2 vector space generated by orbit sets. So orbit sets is just sets consisting of pairs alpha I, which are distinct embedded Reeb orbits, and Mi are non-negative integers. And Mi should be 1 if alpha I is hyperbolic. In this definition, hyperbolic, the eigenvalues of the linearized Poincare map lives on the real line. And also, we fix the singular homology class. So the total homology of alpha, which is all the homology concentrating the orbits, counting with the multiplicities, should be gamma. So that's the chain complex, and we need to define the differential. So differential, it's standard count of geolomorphic curves. But to this work, here we count geolomorphic curves in the symplectization which converge as currents. So we have y here and y here. So r times y. And then we have orbit sets here, say alpha, and another orbit set here, say beta. And then we count some geolomorphic curves in the symplectization. Something like this. We could also have something like this. Can have genus. But the miracle here is the magical number called ECH index. So for a curve, we have the topological number associated to it, which is called ECH index. And this is the guy here. It makes everything work. And Hutchins and Taubes proved that the differential defined this way is well defined, and it is really a chain complex. So d squared is equal to 0. This is high technical and quite hard, but it works. And then Taubes also proved that despite of the choices, we choose a non-degenerate contact form, a generic almost complex structure. It doesn't depend in the form or in the almost complex structure. just in the just in the contact structure psi, which is the kernel of a contact form, and in topology. So in fact, this is isomorphic to another homology theory called Symplectic Topology homology, defined by Kronhame and Mrovka. Okay, so it's quite standard these days. And then we can define the ECH spectral invariants. So the homology itself doesn't depend on the contact form, just on the contact structure, but we can define contact invariants depending on the form. And then how we do this? So we consider the subchain complex generated by the orbit sets with fixed action range. So for orbit set alpha, we define the action to be the sum of all the actions, and action of a Reeb orbit is just integrate the form over the orbit. So we fix an action range, like a t, a real number, and consider all the orbit sets that has action less than t. This is a subchain complex because the differential decreases the action. And then you can look at the homology. We denote this by ECH with the t. And Hutchins et al. Proved that it does not depend on the complex structure, but of course it depends on the contact form. And in that setting, we can define the ECH spectral invariant. So roughly speaking, given a ECH class, so it doesn't depend on the contact form, you can look for a fixed contact form, non-degenerate, and how much action you need to express this like in a real representative. So formally, it's the infimum of real numbers that you can see the sigma, the homology class, inside the image of the inclusion map. So for each L, you have this inclusion map. This is the inclusion map, and then the induced map in homology, and then roughly speaking, is just as I described. For a non-degenerate contact form, you just looked at how much action you need to find a representative for this class. And then for a degenerate contact form, you don't have the chain complex well defined, but you can approximate with it with a non-degenerate contact form, which is also called bumpy sometimes. And the limit is well defined in C0 topology. But as long as you don't change the contact structure. So you multiply, for instance, the contact form by a positive function. So that's how it's defined, and that's how you can try to compute by limiting. And this number has nice properties. So the first one is that I'm going to mention today is the spectrality property. So every ECH spectral invariants are finite. And then, in fact, they can be written as a linear combination of actions. So this is really just some sums of actions of real Reeb orbits on your manifold, but nicely picked. And then the second one here is the conformality property. If you multiply by a real positive real number your contact form, your invariants are also multiplied by the same number. And the third one today is the monotonicity. And if you have a symplectic cobordism, which is exact in that sense, the symplectic form is exact, and it has boundary on two contact manifolds. If these manifolds are non-degenerate, you'll have a cobordism map arising from Symplectic fluid homology. And Hutchins and Taubes studied this map and proved some nice properties. Here I'm calling this map phi x omega. So this is a map that goes from the ECH, from the positive part of the boundary of x, and goes to the ECH of the bottom part. And we have this type of monotonicity. I'm being a little bit sloppy here. Maybe it's better to fix the homology class like being 0, or asking some more properties on x, like x being the product of 0, 1 with the same contact form. But in nice settings, you have the map and this property. Okay. And we also have an additional structure on ECH, which is called the U map. So it's defined similarly to the differential, but instead of counting ECH index 1 curves, we now count 2 curves, ECH index 2. and passing through a generic fixed point here, which is not on a closed Reeb orbit. So this gives rise to a degree 2 mapping on homology, and it turns out that it doesn't depend on the contact form, neither on the almost complex structure. Yes. And another property of ECH spectral invariance, this is more surprisingly, I think that Michael Hutchins, which is here, defined, conjectured this previously, and then with other two students, then Christopher Gardner and Vinny Ramos, they proved this amazing property. So if you have a torsion condition on this cohomology class, which is a condition that you can define a grading on the homology, if this is torsion, and you have a sequence of elements with grading going to infinity, you have this nice property here. So the sequence of ECH spectrum invariance squared over the degrees recovers the volume. Okay. And a consequence is that there exists a sequence of non-zero classes. We usually call this sequence a U sequence because of this property. U of sigma k plus 1 is sigma k. And we have this sublinearity here. And again, I'm cheating a little bit here. We borrowed the existence of a sequence like this from the Seibel-Witten Floer cohomology. But we have a sequence like this. And we can always find a gamma such that this condition holds. So the hypothesis is pretty weak. Okay. So I selected some results using spectral invariance properties here to try to convince you all that this is really useful and fruitful, but I don't need if it's necessary because now it's kind of famous. But yeah, Christopher Gardner and Hutchins proved a refinement of Weinstein conjecture in 3 dimensions. So there exist at least 2 simple Reeb orbits on Reeb flows in 3 dimensions. And then Christopher Gardner, Hutchins, and Pomerleano proves under some hypotheses, non-degeneracy and a torsion condition in the contact structure, that you have 2 or infinitely many. And also Christopher Gardner and Mazzucchelli, Marco is here as well, and proved that you can characterize Bessey contact flows. I think that Marco defined, yeah, he defined. Bess means all the Reeb trajectories are closed, and they characterize this just looking at action in spectrum. Again, all of these results use the asymptotic property, the volume property of ECH spectral invariance. And then Christopher Gardner, Umberto Orinevich, Hutchins, and Liu, they use, again, this property now to describe the following. If you have a Reeb flow, a manifold and a Reeb flow with just exactly two Reeb orbits, you can use the volume property to conclude how the orbits rotates the contact structure, and in fact, this needs to rotate irrationally in an irrationally way. So the orbits are elliptic, and you can understand the flow almost completely. I can't say completely, maybe. This is pretty recent. And also we have this other recent result by Hutchins. So a quantitative closing lemma for 3D Reeb flows. Actually, Michael defined another sequence of invariants, but you can prove using ECH spectral invariance as well, the same result, because he used this volume property there. And quantitative closing lemma is like how much you need to perturb a contact form to find a closed orbit with an action range, within an action range. So these are some nice results that we have. And Michael Hutchins also defined a distinguished sequence of ECH spectral invariants. It is called ECH spectrum. And this is just defined in the case that the empty set represents a non-zero homology class on ECH. So I said that the generators are orbit sets, but I didn't exclude the case of the empty set. Empty set is an orbit set by definition. And there are some nice cases that the empty set is real non-zero classing homology, and an useful one, to be said. For instance, if the contact manifold is symplectically fillable. And then you can define a sequence. Hutchins defined it that way. So this is the minimum of the ECH spectrum invariance. But for the classes that if you apply the UMAP k times, you recover the class of the empty set. So this is a kind of strong condition, and these values can be infinity. It can be infinite because you don't need to have a homology class satisfying this property, right? But we have, it turns out that we have in nice cases. Okay, so the volume property in this case translates into this. So if the CK, now here I'm calling this ECH spectrum sequence, are finite, then you have the volume property described this way. And that's just because the UMAP has degree 2. It's just a corollary from their theory, which is in the paper there. Okay, so the first example. We take the standard tight contact structure on S3. It was already defined this week. You consider the standard Liouville form on C2, R4. This is given by 1/2 xy dy minus yi dxy. And then you restrict this to S3. And this is a contact form. And the psi 0 here is the kernel of it. And you can compute the ECH of this contact structure. And you have at least 2 ways to do this. The first way that Michael did in the lecture notes on embedded contact homology is to consider the irrational ellipsoids that we heard this week already. So you have just 2 orbits, they're elliptic, and then by grading and ECH index reasons, the differential is 0 for any almost complex structure. And then you just need to prove that the ECH index gives a bijection within the generators and the non-negative integers. So that's a way to do this. And this is completely written in the lecture notes that I mentioned. But the other way to do this is a different way. You consider this contact form, which is pretty degenerate. So for this contact form, we don't have a well-defined ECH chain complex because this is super degenerate. Like this is ZOL. So all the Reeb trajectories are closed and has the same action. But for this type of flow, you have the S1 action given by the Reeb flow, and the quotient is a smooth manifold. And in this case, this is just the sphere, the 2-dimensional sphere, because this is just a Hopf vibration. And then you can consider a Morse function here with just 2 critical points. And you can follow bourgeois argument and perturb a little bit the contact form in a way that you keep in the same contact structure. You can pull back the function to S3, and then you perturb that way. And then for each t, real number t, you can find an epsilon such that for this new contact form, every orbit with action less than t corresponds to a critical point. So any orbit set for this form, and the form is non-degenerate until this action. So for this contact form, you have orbit sets like this. So we just have 2 orbits, and you can look at these combinations. And you, in this setting, you obtain a well-defined directed system, depending on epsilon and t. But in fact, t and epsilon can be, they are depending each other and have nice iterations. And then you can follow an argument due to Nelson-Weiler and for precondition bundles, and compute the full ECH homology by a direct limit here. So that's right like this. So you send epsilon to 0, something like this. And you just need to prove that the ECH index gives a bijection again. But the advantage of this method is that you can compute the UMAP here. For the irrational ellipsoid, I don't think so that people can compute the UMAP. At least I don't know, and I never found it in any place for any irrational ellipsoid. But for a irrational ellipsoid which is close to the S3, to the round and tight one, and you can compute the UMAP, and here you can compute the UMAP with similar methods. But it turns out that the UMAP doesn't depend on the contact form because of Taub's isomorphism, and then the UMAP is really an isomorphism sending the 2k degree generator to the 2k minus 2 generator. And moreover, for a complex ellipsoid, which was defined already this week, we can compute the whole ECH spectrum. And since we just have one singular homology class, this is simply connected, these are all the spectral invariants that we defined for this example. So NAB here is the sequence of linear combinations, MA and B, M and N non-negative integers, but this is ordered in non-decreasing order, and this is the whole sequence. So these are the CK here, and in particular, if A and B are equal, you have a ball of action or capacity A, and then the sequence is just like this. So 0 and A 2 times, 2A 3 times, 3A 4 times, 4A 5 times, and so on. So that's the first example. I would be glad if you have any questions. Stop a little bit. Okay, so the second example is almost the same, but it's my favorite one. We have the real projected 3 space, and you can, since this form is invariant by antipodal map, you can descend this form to another form in RP3, and the contact structure as well. So you have a contact form in RP3, which is similar to that one that we just described. And the orbit space is, again, a sphere, so you can do the same approach here. And in that case, you conclude that the ECH is given by 2 copies that of the previous one. So you have one element, a generator, for non-negative even degrees, but for each singular homology class. So it's something like 2 copies of the previous ECH. And in fact, I think that there's a relation of the finite covering map and the embedded quantum homology, but I don't think that anybody has written it out, but I think it works. Maybe one can think about it. Like if you have a covering map that respects some nice relation with the contact forms, you should have a relation in embedded quantum homology. But for this example, we have another viewpoint. So I should recall this. So RP3 is known to be diffeomorphic to the unit and tangent and cotangent bundle of S2, the round S2, with the round metric. And in fact, any contact form such that the kernel arises the standard contact structure can be related to a fiber-wise star-shaped hypersurface in the cotangent bundle of S2. So this is almost the same exercise that Miguel just told us about star-shaped sets in R2N and contact forms on the sphere. So fiber-wise star-shaped. And this is in fact a bijection. Here fiber-wise star-shaped mean that you have the 0 section, and on each fiber this is a star-shaped. So it could be convex like this, but it also could be something like this. So each ray arising from the 0 section hits once and transversally the boundary. So in particular, if you have a Finsler metric, the fibers are convex sets, and if you have like bounds convex sets, and if you have a Riemannian metric, this is just ellipses. And so if you have a metric on S2, have a contact form on RP3. And the Reeb flow is the geodesic flow. Okay. So a nice approach is to consider the Katok-Finsler metric. And I didn't mention, but you can repeat the argument and compute the UMAP, and the UMAP is an isomorphism. It's exactly the same of the previous case. So the Katok metric is the following. So you have the round metric, and you have the direction of the wind here, and you perturb the round metric with this direction. If you perturb sufficiently small, it is still metric, but it's irreversible now. So if you go through the equator in a direction or in another, it makes difference, because if you're running in direction of the wind, you run faster, right? But if you run in the opposite direction, you have the force of the wind. So you have a reversible metric. It's not a Riemannian metric, but it still has nice properties, and in that case, equators are still geodesics, and if you perturb in an irrational way, so take A to be an irrational number, say that small enough, and not 0, because here is the round metric. Equators are the only geodesics. So you have two geodesics, which corresponds to the equator in the direction and in the other direction. And then we have exactly the same setting to the irrational ellipsoid. And it turns out that the covering map that sends S3 to RP3, the double cover, when you lift the Katok-Finsler metric to the S3, this is our ellipsoid. So that's why it's pretty similar. And in fact, you can compute the ECH spectrum if you play enough, as I did, because I was full of things to do. And then I compute the ECH spectrum for this metric, and this is related to the ellipsoid, as it should be expected. So this is the length of equators in this metric. So you could be faster in the direction of the wind, or slower, going in the opposite direction. And then this M2 here is, you consider this sequence, NAB, and M2 means that I consider just these weights that sums to an even number. So M2 means like multiple of 2. It's a bad notation, I'm sorry about that. But yes, that is the ECH spectrum. But what about the whole ECH spectrum invariance? So ECH spectrum use the UMAP, and you need to iterate and recovers the empty set. So this is about null homologues orbit sets. So if you consider just a set form consisting on just an orbit, like alpha is gamma 1, 1. So this is an orbit set. And in fact, this corresponds to a non-zero homology class to the irrational Finsler metric, for instance. And non-zero singular homology and non-zero ECH element. And then the ECH spectral invariant of this guy is just the length, because the action is the length. So you consider this sequence. The even multiples corresponds to the orbit sets with null homologues, zero homology class. But the odd multiples, if you sum m and n, and it is odd, it's again spectral invariant, but corresponding to an orbit set which has like homology class 1. Okay, so if you put a 0 here, and you can do this because the CH spectrum is kind of continuous, you recover the case of the round metric, and by a classification due to ABHS, Abondandolo, Braham, Irnievich, and Salomon, we can conclude which are the ECH spectrum for any Zoll contact form on RP3. So if you have a Zoll contact form on RP3, and you have this minimal action, this L, so this is the action of a simple orbit, this is the sequence of the ECH spectrum. So 0, 2L, 3 times, 4L, 5 times, 6L, 7 times, and so on. And the reason that is just even numbers it's because for the round metric, you need to go twice to obtain a contractible orbit in the unit tangent bundle. Okay, so again, if you have any question, I would be glad to answer. So we have, in the paper of Dan Christopher Gardner and Marco Mazzucchelli, they also proved that you can characterize the Bessey contact form just looking at the ECH spectrum invariants. So they proved that a contact form is Bessey if and only if you can find some non-zero element in the ECH such that the ECH spectrum invariant for this element is equal to the ECH spectrum invariant for the U of this element. So the U map doesn't change the invariant. And in fact, it has to hold for infinitely many sigmas, infinitely many elements. And one can ask if you can do something similar to Zoll contact form. So Zoll means all the trajectories are closed and have the same period, and the Bessey just that all the trajectories are closed. So if you look carefully in their proof, Marco and Dan, they prove that the thing that I said, but if C sigma is equal to C U sigma, they prove that this is Bessey. But actually, if you add this hypothesis here, if they agree with the minimal action, you can prove that this is Zoll. And it's just two small changes you need to do in the argument. And the question is, does the converse hold? Because they characterize the Bessey one. And just by the examples that I showed and the characterization due to ABHS, so this is for the S3 and this is for RP3, I think. And by the computation that I just showed, the answer is yes for S3 and RP3. So a similar story holds for any length space. It's kind of an exercise to do this. But I don't know, I don't have any clue to how to prove it for other manifolds. But I believe that it should be true. So I think that if it's Zoll, this also holds. But it's still open. A related result is Ginsburg, Gurel, and Mazzucchelli. So Victor and Bashakis are here as well. They characterize Zoll convex contact spheres in any dimensions using Eklund-Hofer capacities. But just here, you need the convex thing. And maybe, I believe here for any type of contact forms, in particular for star-shaped spheres in R4, but just in dimension 3 because we are talking about ECH. So that's a thing that I started to think maybe a couple of months ago, but I don't have any comment. Okay, so a similar story holds for the ECH spectrum. So Michael Hutchins proved it also in the paper of the quantitative closing lemma that if you have the equality CK and CK minus 1, and then every point is contained in a closed Reeb trajectory with action at most CK. So an immediate consequence is that if you force C1 and C2 to be the minimal action, then every orbit is contained in the minimal action, in a minimal action trajectory, so this is all. Okay, but what about the converse? So we saw that for RP3 and the standard contact form, this is just the round metric on the sphere. C1 and C2 must be equal to 4 pi because you need to go twice in a simple geodesics. But this is 2 times the minimal action. So the converse in that setting does not hold. But even so, C1 is equal to C2. So next question. I'm sorry to bring in more questions than results. Does C1 is equal to C2 force lambda to be Zoll? I would say yes, but I don't know how to prove it again. Oh, okay.
The statement at the top, this wasn't known before 2022. I feel like it might have been just an artifact of Daniel Marco's.
Maybe maybe it's my bad, but I just found this in this paper from Michael, and indeed he did this for these new spectral invariants But the same proof holds for the ECH spectrum. And maybe you can tell me about this if it's known before. I'm sorry about it. Okay. Maybe Marco and then argument already proved this. Okay. Now, a nice example. So, is that true that the minimal action is always a ECH spectral invariant? It could be, but it turns out that it's not true always, so I'm going to show an example. So together with Vinicius Ramos and Alejandro Vicente, Alejandro is also here, and Vini unfortunately not, we proved the following result. So consider a sphere of revolution, and here a sphere of revolution is, you consider a planar curve in R3, let's say a graph of a function, so something like this, with unique critical points. So a critical point gives rise to a geodesic, which is called the equator. So you rotate this around a fixed axis, let's say the z-axis. And a unique equator means just one critical point. Then we prove that there exists a toric domain that when you remove, let me draw this again. When you remove the north pole here, the upper point, and consider the disk cotangent bundle, this must be symplectomorphic to the interior of a toric domain. We proved this, and actually we can say further and a little bit more for some examples. So consider an ellipsoid of revolution. So you consider a triaxial ellipsoid, elementary one, and then when you have two parameters equal, this must be of revolution, and then you can normalize. So let's take 1 and 1 and C. So we have the three axes, one with size 1 and one with the other C. And for this type of sphere of revolution, we can compute the toric domain. I mean, we can draw the region. So a toric domain is something like this. You consider a region here and lift it to R4 via the moment map, which is like, so this is the moment map of the standard torus action. You can lift it to C2. So a toric domain is something like this, a pre-image of a region in the first quadrant. So for the ellipsoid, we can draw all the pictures. So if C is lower than 1, the region is that funny region here, which is nor convex nor concave. And I think that this was the first toric domain raising naturally or in an interesting way, that it not like you just draw it and, oh, consider this toric domain. So this is really a thing. This is the ellipsoid, which is nor convex and nor concave. But for C equal to 1, this is just the round sphere on R3, and this agrees with the previous result together, Vini, and that it must be the polydisk. So the toric image is the square. Here is 2 pi, which is the length of the geodesics. And then if C is bigger than 1, you are considering like this prolate and or elongated ellipsoids. And the toric image is like this. So this is maybe an edge of a sphere or something like this. And this is a convex region, right? So we can do this. And the parameterization here is given by elliptic integrals, but the draws are nice. And this corresponds to the example that I want to tell. So I want to find a contact manifold that the minimal action is not the ECH spectral invariant. Okay, so that's this remark. Consider a Liouville domain, and it's not hard to prove that the Gromov width, which measures the biggest ball that you can embed symplectically into a symplectic manifold, must be lower than or equal to any ECH spectral invariant of the boundary. Again, I'm being a little bit sloppy here, but you can consider like the singular moduli class to be 0, and so this is definitely true. And for our examples, this is just spheres, so it is simply connected and everything works. So if the minimal action is a ECH spectral invariant, it should be greater than or equal to the Gromov width of the filling. And in this example, if you put C bigger than 1, so you have this elongated ellipsoid, and you can check that the minimal action is 2 pi because this is the length of the equator. But the Gromov width, it turns out to be bigger than 2 pi. And in fact, we can compute the whole function, which is the Gromov width depending on the parameter C. And that's the graph that we have. So from 0 to 1/2, you have this curve which is given by elliptical integrals. And this is just the length of a geodesic that just exists for C smaller than 1/2. So this geodesic oscillates among the equator, and this length is exactly the Gromov width. We proved this. And then when C is equal to 1/2, 1/2, this geodesic collapses into the equator, and so the length is 2 pi, and the Gromov width is 2 pi, and it keeps being 2 pi until you hit the round sphere. And then from the round sphere to the value that the meridians are smaller than 4 pi, you have the length of a meridian. So this is not linear. I'm sorry if it looks like linear, but it's not linear. This is the third elliptic integral, so exactly the length of a meridian. And then you reach 4 pi. So 4 pi is exactly twice the equator, and then it stabilizes. The Gromov width is 4 pi forever. So for that example, the Gromov width, it's bigger than the minimal action, but you can say, no, but this is not a smooth contact manifold, the boundary of this toric domain. Yeah, you're right, because I just showed the picture that this is like a sphere, but definitely you can consider something smooth really close to this, and if it's C1 closed, everything will work fine. And you have an example of a Liouville domain in C2 where the minimal action is not the ECH spectral invariant of the boundary. So it's not always true. Any questions? Comments? Okay. So a result in dynamical setting. I have more results in symplectic embedding problems, but this workshop is in dynamics, so I try to do this thing, and that's the reason that I bring more questions than results. I'm sorry about that. But yeah, we can find elliptic Reeb orbits for some contact forms on RP3 using ECH. So I have this new definition here. Maybe it's a terrible choice, but I defined a linearly positive contact form if the Conlagenda index is always positive. So for a contractible orbit, you can extend and take up a trivialization that you can extend to the disk, a trivialization of the contact structure. And with respect to this trivialization, I'm asking for all the Conlagenda index are 0. For instance, to a global trivialization. So this is the theorem. Take a non-degenerate linearly positive contact form on RP3, defining a tight contact structure. You can think just about the standard contact structure. That's not a problem. And then suppose that every Reeb orbit with Conlagenda index 2 is embedded. So there are no multiply covered orbits with Conlagenda index 2. Moreover, suppose that the C1, so the first value on the ECH spectrum, agrees with the minimal action among the null homologous orbit sets. So that's why the 0 here. So you are considering orbit sets where the singular homology class is 0. Okay, so in that case, then you can find an elliptic Reeb orbit with Conlagenda index 1, and the action must be in this interval. So that's the result. I think I have time to explain. It's a little bit simple, but use some results and the magical machinery, which is ECH. So we've seen that we have a generator for each even non-negative even degree on the ECH of RP3. So let this guy be the generator of ECH on degree 2 of RP3. Sorry. Let's say curl lambda and 0. So we also think that the UMAP sent this to the generator of degree 0. So the empty set, it turns out that the empty set is non-zero here because RP3 is fillable. And then this fact gives rise to a curve, C, a J-holomorphic curve for a generic symplectization admissible contact structure that has the property that Fredholm index of C is equal to 2 because the ECH index is equal to 2 and the embedded part and connected part, Michael proved that this must have Fredholm index equal to 2. And under the hypothesis of the contact form being linearly positive, you can conclude that C must be of this type. So this can be a torus with one puncture with Collins-Ender index 1, here, the orbit. Or it could be a cylinder with two positive punctures with Collins-Ender indices 1, 1. Or it could be a plane with one puncture and Collins-Ender index 3 orbit in the positive end. So C must be one of those ways. So for the first and second, we are okay because of this hypothesis on the Collins-Ender index 2 orbits. I mean, if it were hyperbolic, you can go twice, and you would obtain a orbit which is not embedded but has Collins-Ender index 2. But for that case, this case, we need to conclude that this is multiply covered, and hence it must be elliptic. The action I can explain later. It's simpler. So if it were simple, from the fact that C1 is equal to A0 mean, you can conclude that the connected component of the moduli space of these planes is compact. And in fact, you can prove by a criterion that is known, like in the paper of Hutchins, Christopher Gardner, and Pormeliano, that this projects to a disk-like global surface of section in the manifold, like on RP3. And in that case, the boundary would be an orbit with self-linking number -1 and Collins-Ender index 3, and simple and contractible, obviously, because this is fillable by a disk. And then this is a disk-like global surface of section, and you have an open book decomposition of the manifold, and by a result of Hoffe, Vysotsky, and Zender, this concludes that RP3 is the type 3 sphere, which is a contradiction. RP3 is not diffeomorphic to S3. And then what's the problem? The problem is, I suppose that this is simple. So this can't be simple, so this is multiply covered. So even in that case, if you just go one time in this orbit, it must be elliptic and has Collins-Ender index 1 because of the behavior of the iterates in Collins-Ender index. So one of these orbits are elliptic and exist, and the action is just because C1 is defined by the minimum that you can find a class that when you apply U to this, you recover the empty set. So it must has action, these guys has action A0 mean, so it could be A0 mean over 2, for instance here, but it could be the full A0 mean. So you can conclude that the action is in this interval, in that interval, but just a remark, since pi1 of RP3 is Z mod 2, A0 mean is lower than or equal to 2A mean. So this elliptic wave orbit that exists has action between the minimal and twice the minimal. Yeah, that's an idea. And this is not the first result about those things. The first that I know is by Miguel Abreu and Leonardo Macarini. They proved that any dynamically convex contact form RP2n plus 1, even the degenerate one, and if in any dimensions, has an elliptic wave orbit. And you can say something about the index as well. And for length spaces, they study strictly convex contact forms and prove similar results. I think that the main tool here is symplectic topology, positive equivariant symplectic topology. Yeah. And Humberto and Pedro Salomão, they also had this more general result than mine, I mean. The contact forms seem infinitely close to dynamically convex ones. They admit parabolic elliptic Reeb orbit, and they can conclude about the self-linking number, which is -1/2, like this case. And they conclude about the transverse rotation number, so, and hence about the convex and the index. Yeah. Oh, okay. So sorry.
So your theorem can be proved using equivariant symplectic.
Yes and no, because here I suppose this embedded thing, and I give an estimate on the action.
Cannot be an iterate, right?
Yeah.
So by equivariant symplectic topology, you must have a periodic orbit within x1. If it's hyperbolic, then the second iterate has index 2, and it's not embedded.
And what about the action of this orbit?
Not about the action.
Okay.
Yeah.
Oh, I see. Yeah, you're right. You're
I'm
right.
not sure about the action, but if you don't care about the action, then it follows from equivariant symplectic topology.
Yeah. Yeah, I agree.
About the action, I have to feel.
Yeah. Okay. So it follows also from symplectic topology techniques, but here we can estimate the action. Of course, we suppose something related to the action. Yeah. Okay. So a nice question would be, when does this property hold? Because maybe I'm asking too much, but for which contact form it holds? So I'm sorry about that. I don't know, but I know how to answer it in some case. So we've seen that in Zoll contact form it holds, and ellipsoids of revolution in the paper that we proved this. You can also check this. And in my example of contact of Katok-Finsler metrics that we just described, it also happens. And for a wider, broader class, which is famous in differential geometry, which is metrics pinched by 1/4, I can also prove this. So consider a Riemannian metric on the sphere, which is pinched by 1/4, which means this modulo rescaling. And K here is the sectional or Gaussian curvature. So in that case, I can prove that the first value on the ECH spectrum is the A0 mean, so the minimal action among all the null homologous orbit sets, and this coincides with 2 times the length of the shortest closed geodesic. So 2 times the A mean, the minimal action. And moreover, by famous estimates, Klingenberg and Toponogov, for instance, you know that L, the shortest closed geodesic, has length between 2 pi and 4 pi. So that's the result. I don't know how to answer this question in general, but I know how to answer in this case. And for this case, in the bumpy case, the non-degenerate case, you can prove actually that the orbit set consisting in the shortest closed geodesic and the Reeb orbit corresponding to the same geodesic in the other direction. This is closed and non-exact in homology. So this corresponds to a non-zero element on ECH under this hypothesis. And then for the non-degenerate case, you can just check that this holds using Toponogov and Klingenberg estimates. And then for the degenerate case, you just use the continuity of the Birkhoff min-max values, because you can realize this L as the Birkhoff min-max value. This is positively curved, and everything works fine. You can take a sequence of bumpy metrics converging to the degenerate one and use this continuity. So that's how you prove this theorem. But actually, Harris and Paternane has a result that has maybe 15 years. That implies that in this pinching condition, the contact form on RP3 is dynamically convex. So one could wonder or even conjecture that this holds for dynamically convex contact forms. I don't know if it holds, but I would say that it holds. But I don't know how to prove it, and maybe Michael Hutchins, Humberto Nievich, and Vinicius Ramos have a result in this direction. I think that they are still writing the details, but I think that it's a related result. Okay. Any question here? Okay. So to this end, I just want to finish. I will try to just say a little thing to be quick. So we can also obtain systolic inequalities using ECH spectral invariants. And I started to think about this like last month, but I tried hard just to say this here because it's a dynamic conference. And I'm sorry that I don't have a nice result, but I can't use ECH spectral invariants to give this systolic inequality. So as I said, if you consider fiber wires as star-shaped hypersurface in the cotangent band of S2, the tautological one form restricts to a contact form, and then you can ask, how about the minimal action of the Reeb orbits? And then the story follows similar to, follows from the properties that I mentioned. You can use the monotonicity to put these guys in a bigger round metric, but for the round metric, we computed all the CH spectral invariants. And this is a natural symplectic cobordism, so the monotonicity holds. And then the minimal action among the Reeb orbits should be lower than or equal to the ECH spectral invariant for the round metric. G0 is the round metric. And obviously, the star-shaped hypersurface is compact. I admit it's compact. And then it's enclosed in a round metric like this. So we have this systolic inequality. It could be terrible because for star-shaped, we could have a star with a huge leg, but it should be star-shaped. So this inequality could be bad, but could be good. I don't know. So one thing that I'm trying to do now is estimate this big R, which is like the maximum circular radius over the fibers, using the curvature. It would be amazing to do this. Like if you can do for pinching by 1/4, it would be amazing to give a systolic inequality in this case. So just to finish, I want to mention that there is a symplectic embedding problem related to this. It's just if you wonder, oh, what's the minimum of the radius we need to take to embed a disk cotangent band of a metric into a round one. So by monotonicity, you have a systolic inequality related to this. And maybe one can find nice systolic inequalities in this setting. As I said, maybe with pinching conditions. And to be fair, we have a lot of results in that direction, not in symplectic side. So it starts with Croak, which was the first bound for a Riemannian metric on S2. And then Rotman, Saborao. For instance, Rotman proved that the length of the shortest closed geodesic on the sphere should be lower than this number, 4 times the square root of 2, twice the area of the metric. And then the first symplectic result in that direction was given by the BHS. So this couple of results are amazing. If you pinched by 0.83, meaning that you're very close to the round metric, you can prove that the shortest closed geodesic has a length bounded by this. And this is sharp, because any zoometric with these pinching conditions, for instance, the round metric, has the equality here. And they prove this is equivalent here, bit Zoll and equality here. And also they prove this sharp systolic inequality for any Finsley spheres of revolution. And they use symplectic techniques. So Humberto and Alberto, Nievich and Abondandolo told me that maybe one can conjecture that it can go to 1/4. So 1/4 is 0.25. It's kind of far from this number, but it would be nice to try to prove this. Maybe this follows from this symplectic embedding problem. I don't know, but I don't have any clue. And we also have different results comparing to the diameter instead of the area of the sphere. I'm sorry from this rushing tool less slides, but that's all that I want to talk about, and I'm stopped here.
Are there questions?